Good afternoon. My name is Reznik, and let me start with a short introduction. This is my picture, and I'm using this one to demonstrate that a real picture could be a little bit different from one which you had in database. So your biometrics should be really good to catch it. But where should be, I'm a professor of computer science at Rochester Institute of Technology. I have been there for 20 years, and I hope maybe we have a few of our alumni in this room. Maybe they're just coming a bit late. I'm a faculty member of the Global Cybersecurity Institute, which we do have at RIT too, so you're welcome to start thinking about us and maybe start thinking about how to collaborate with us. And we will be trying to convince you that we are worth your collaboration. And let me introduce our lab. We have a lab on data quality and intelligence security. And I have a few PhD students. One PhD student, Igor, probably you remember him. He presented here a few years back, just pre-pandemic. I understand nobody can remember that. And another one is Sergey Chuprov, and he is graduating this year and looking for a job. So if you can help, please talk to him. And by the way, beyond those two, our lab graduated 58 master students over the last 5 years and more than 100 over the last 10 years. So we are pretty active, and again, our students are around. Just to continue, a very short introduction about my teaching. As a professor, I have to teach, and actually I like it. This is the courses which I have been teaching over the last 5 years. You see, most courses combine security and AI, and these two areas actually were my field over the last 20 years. I have developed a couple of those courses. And last year, my new textbook, Intelligent Security Systems, How Artificial Intelligence, Machine Learning, and Data Science Work for and Against Computer Security, was published by Wiley and IEEE Press. And by the way, it's available at IEEE Explorer. If you do have a subscription, or your organization has a subscription, it's for free for you. And just again, very little about our research. We are trying to do different projects, and again, most of them combine artificial intelligence and security, and we are working with other universities, and we got funding from different federal agencies, which doesn't stop us from developing real software products. We developed a few Google applications, which on security, data quality, evaluation, which are available on Google Play, again for free. And now, finally, I can talk a bit what we are going to talk about today. We are going to talk about federated learning. I'm not sure if you heard about it. This is relatively new methodology and technology, which was proposed by Google about 6 years ago, so it's relatively new. But why I want to talk about it and why we are trying to do research on it, because I believe this technology introduced real revolutionary change in AI attitude towards security. So again, probably I tried to walk around today and talk to different people selling different products, and I was not able to find any product which at least didn't claim that they used AI. So everyone is using AI right now, and that's very good, because 15 years ago, I remember when you were talking to security people, networking people, system administrators, all of them thought, really, we don't use AI, we don't need it. So now it looks like everyone needs AI, and security does need AI. And again, we are trying to develop AI solutions for security. That's one side of the story. Another side of the story, it appears that AI probably has to be more secure and safer. And again, everyone started talking about it. And we heard the presentation here, whatever, half an hour ago, and people are talking about it. And that's another side of the story. We have to make AI more secure and safer. However, again, the movement over there has not advanced so far yet. And that's why I believe we need new approaches to AI and to machine learning. And that's what federated learning is about. The basic idea, and Sergey will be talking in a couple of minutes, and he will provide much more details, but the idea of the federated learning is that, again, it's some kind of revolutionary change in machine learning. And you remember, machine learning learns from data. So if I have multiple sources of data, say each of you can give me some data, what should I do to learn from all of you? I'll take data from all of you, get to me, to some kind of server point, aggregate this data, and train my model, and learn from your data. That's how machine learning has been working so far, conventional machine learning. There are a couple of problems. Problem number one is technological, because I have to communicate this huge amount of data through networking. But again, technology gets better and better. I have to get a lot of resources on my server too, but again, technology gets better and better. But the point is, all of you are nice guys. You want to collaborate. You want to develop together better knowledge and better model. But you might have some limitations in sharing your data, because when I'm asking you to transfer your data to me, you may say, I want to collaborate, but I wouldn't like to give out my data, because it's not really my data, it's the data of my clients, and they will be not happy. And by the way, why should you move your data to me? That's not good, because as soon as you move your data out, privacy is lost. That's it. So what is alternative? And again, federated learning offers an alternative. In federated learning, data never leaves the source. So you keep your data for yourself. Never give me your data. I'm not asking for it. But you start training your model, your local model, based on your data. And you develop your own model after some training. Your model could be not perfect, because whatever is very localized, you're using just your data, and you don't have a lot of data in comparison to all of us. But the model is maybe more or less reasonable. So next step, you share your model with me. Not your data, but your model. You give me your model, I'll take all your models and aggregate the models and develop global models based on all your local models. So this way, this global model actually is developed based on all the data initially. But you keep your data. I've got this global model. I send it back to you, and you continue training this global model based on your local data. Then, after some training, we repeat it, and we do it in rounds. That's the idea. And that's, again, conventional federated learning so far. Again, the first application was developed just 6 years ago, and that's what people are doing now, investigating different opportunities. Now, we started thinking about, okay, that's great, that's revolutionary change because, again, privacy is protected, security is improved because data doesn't communicate, so I don't have to protect it over communication. Everything is much better. But I know that all of you are good guys, but there could be bad guys just in that room. And that guy might try to spoil the process. He might try to give me a bad model. And in this case, whatever, I will use this bad model along with all you good models, and my global model maybe will be not that good. So should I take his model? Probably not, right? Next thing, again, what I'm in federated learning, again, I'm sending global models back. Global models are supposed to be better than local models. So I'm sending back this bad guy a good model. So he is bad, and I'm sending him good knowledge. Why should I do it? I'm helping him to make better attacks against my process, against the whole thing. Probably I should not do it either. And that's what we are trying to do in our research. That's how we are trying to modify this Google initial federated learning model. And again, Sergey will be talking a bit about it. Now, before he starts, you are industry people, right? So we are trying to actually to introduce, we have been trying to work with the industry, and we have investigated 3 different use cases. And again, Sergey will be talking about them in greater details, but let me just introduce them. Case number 1, intelligent transportation systems. Again, I might have different data sources, I might have sensors available on vehicles, I might have sensors available on the roadsides, and I want to use them. And in order to do it, again, I have to communicate them. That's case number 1. Case number 2, completely different from financial organizations. And this is a case for fraud detection. Again, different financial organizations like banks do provide some transactions, but do have some fraud transactions. But they don't want to provide those transactions to anyone. They want to keep them. So we can use federated learning to develop, again, fraud detection model. Based, again, on local models developed at each bank and then aggregated together. And our last case is about medical applications. So again, assuming that you might have different physicians or different companies who took some tests, say X-ray exams, and they want, based on those X-rays, they want to develop new model of detecting certain diseases, cancer, whatever. So again, they don't want to share real X-rays because they have to keep them private. But we want to use all this data available from different companies to develop a good detection technique. And again, that's another possible application. Now, I'll pass it on to Sergey, and he will introduce himself. But before he does, just one more thing. Today is his birthday. So please don't be too harsh on him. And I hope he will win a couple of prizes today.
Yeah, hopefully so. Yeah, hello everyone. I hope you can hear me well. Yeah, I can try to put it up. Is it better? Okay, thank you so much. Yeah, so my name is Sergey Chuprov. Thank you very much, Professor Reznik, for introducing myself. So I'm a PhD student in Computing and Information Sciences at RIT. So my advisor is Professor Reznik, and my research interests are the security of artificial intelligence and machine learning-based systems, the data quality, and security assurance, and improving the robustness of this machine learning and systems, so with the especially those integrated with network facilities, which we are seeing more and more in our today's world. So yeah, let me go to the quick, a really brief introduction of the Federated Learning. So the Professor Reznik has already done this, but yeah, I will try to explain it using this fancy picture. In the Federated Learning, we have the notion of the aggregation round, which involves 4 major steps. So we also have the number of local clients here that you can see here on this slide. Essentially, these local clients might be any kind of devices that you guys use. For example, that might be smartphones, that might be tablets, or that might be any other kind of devices which are capable of maybe collecting or generating the data and to train local machine learning models based on this data. So the first step is the local training, where we train the local machine learning model on these clients. Then on the second step, after the local training, we transmit these trained local models to the thing which is called aggregation unit. And this aggregation unit is responsible for the step number 3, which is the aggregation of all these models. So this aggregation might be performed using some kind of aggregation functions, which usually, in most cases, just averaging of all the parameters of the models. But there might be much more complicated aggregation strategies, which are being actively developed and researched now in the publications. So, and after we produce the global model, after the aggregation, we distribute this global model back to these local units, and then we perform these 4 steps over and over consequently until we meet some kind of termination criteria, which might be the level of performance which we want our model to achieve, or this might be the training time allocated for the training. So, yeah. Let's quickly summarize the major objectives and challenges of the Federated Learning. First, it provides the privacy enhancement because we keep our data safe on the local units, and we never transmit the data, we transmit only the models. And then we also are able to reduce the training time and the computational resources required to train our models, because we do not need to collect the large amount of data, and we can distribute the computations to train our models on these local units. But here we also have some challenges. First, we need to maintain the secure and reliable communication, because we send our models over the network, and we probably do not want the adversary to steal our models from this network. Then we also have to deal with the independently and identically distributed data. So we might have heterogeneous devices, and we might have data of different distributions in our Federated Learning process. And we also need some kind of methods to handle this problem. And there are from the statistical perspective. And the next thing, we also have to deal with the malicious local units, and I will talk about this next in my presentation. So here are the aspects we are going to cover in our talk. First, we investigate the feasibility of this Federated Learning in multiple industrial use cases. Then we provide our recommendations how to train machine learning models more robust if we have the data quality variations. Then we investigate the conventional methodological vulnerability, which we discovered in the Federated Learning during our work, and I will provide some insights on how the adversary might compromise the process. Then we are going to describe our developed FLAME framework, which includes methods and software solutions to enhance machine learning robustness and security during our machine learning process. And also our developments and solutions are reflected in our publications, and we also have a patent application, and we're actively looking for a partnership and collaboration. And if you're interested, please approach to us, so we will be happy to talk about it if you are interested in our research and developments. Okay, so let's go to the first part of the use cases, the intelligent transportation system use case. So first, we need to answer the question why machine learning robustness matters. So robustness to data quality variations is a hard challenge for real-time machine learning applications, especially those implemented in industry. And let me introduce the example with the connected vehicles. So let us assume that we have the vehicle which is equipped with the onboard camera. This is kind of the smart vehicle which can recognize some kind of objects on the road. And let's assume that it's approaches the intersection and it sees the new traffic sign recently installed on this intersection. As you can see, it can successfully detect this traffic sign, and then it also sees another red vehicle approaching the intersection, and it decides to send the image of this traffic sign to this red vehicle over the network communication channel using the wireless network. And in real-time applications, especially in wireless network, we usually use UDP, which is not reliable. And during this network transmission, we have the packet loss occurred, and as you can see, the red vehicle cannot properly recognize the image of the traffic sign because it's too corrupted due to packet loss. And in this case, we can say that the machine learning system installed on the red vehicle is not robust to the data quality variations in the data. So the next question that I want to answer is how to enhance machine learning robustness in execution. And under execution here, I mean already pre-trained machine learning model, which is put into the application. So it's already pre-trained, it's already ready, and it's working in real time. So here in our research, we have two major approaches how to address this problem. First is the reactive approach, and here we're aimed at monitoring machine learning performance during the system execution, and we apply the countermeasures post factum. For example, we can detect that the machine learning performance degrades, and we also can see that the quality of the data also degrades. And here we can do some kind of data cleaning. We can try to restore the data, and if we have this ability, we also can interrupt the machine learning model, collect more data, and do the retraining. So this is the first approach, how we can react on this problem. The second approach is proactive approach, where we are aimed at applying the initial measures before the machine learning model is put in place for execution. And here we can apply some kind of methods on the training phase to increase the robustness of the machine learning model. For example, we can try to collect and add more data of lower quality into the training sets, or we can do some kind of adversarial training, or there are other bunch of stuff that we can do in this case. So yeah, let's go to our actual empirical study design. And here, in this use case, we investigated the proactive approach and specifically two strategies. The first one is called the transfer learning, and the second one is federated learning. So here on the right side of the slide, you can see some kind of schematical empirical study design of our use case. And here on the upper side, you can see the part for the transfer learning. And here we were trying to investigate how to better compose the data sets for the model retraining to make it more robust to the data quality variations during the execution. As you can see here, we were trying to compose various retraining sets of the images of various quality. I will talk about a bit later how we obtained these images. And then we were trying to test this retrained model also on the data of various quality. And here you can see on the bottom part of the slides the empirical study setup for the federated learning. Here we also have the data of various quality, but this data is allocated to different data sources, which are local clients in our federated learning. And here we were trying to understand how to better compose the qualities of the data to train more robust machine learning model in the federated learning manner. And here, as our industrial domain, we investigated intelligent transportation systems, and for the data we took stop and the traffic signs images of various quality, and as the machine learning model, we employed the pre-trained VGG16 classifier, which is a really popular machine learning classifier in computer vision, and it's open source. So yeah, here on this slide you can see some examples of the obtained images, and to obtain these images we established a real wireless network, and we transmitted these images over this real wireless network, over this communication channel, and during the network transmission we manipulated the quality of service parameters. For example, in our case, these were the packet loss ratio and the size of the buffer socket. And to make this possible, we used the Powder platform, which is the open source platform maintained by University of Utah. They have their website. You can go to their website, you can create an account, and you can establish your network topology, which includes real network devices allocated over their campus, and you can freely use it. This is really cool stuff for network research if you need. So yeah, this is a very good opportunity to explore. So we used this Powder to establish our wireless network topology between two nodes, and we transmitted these images, and here you can see some examples of the images that we were able to obtain. So here you can see some kind of artifacts, some kind of data loss, and etc. Okay.
I have a quick question.
Sure.
Were those data loss numbers a result of the inherent issues in the wireless network, or did you inject those values?
We manipulated the values. Yep. To obtain this one. Okay. Okay, this is our results on the classification accuracy we were able to obtain after training our models and evaluating these models on the data of various quality. The first case, we retrained our model on the original images, and then we tested it only on the distorted images. So this is this case. In the second use case, we retrained our model on the distorted images only, and we tested this model also on the distorted images only. Then for the retraining, we use distorted images, and we tested it on the mixed set of the original images and also corrupted images. And in the case number 3, you can see that we retrained our model on the mixed images, and we also tested our model on the distorted images only. And as the conclusion from here, we can see that in this case, in the case number 2, we have the better performance in 2 of 3 cases, and the comparable performance in 1 of these 3 cases. And the conclusion here is that this is important to use the pre-trained machine learning model on the comprehensive data set. For example, we employed VGG pre-trained on the ImageNet, which has around maybe 10 million images, and it's also important to retrain it for the data of various quality. For example, if you know that you will have the data degradations in your machine learning system, so it's important to do the retraining using this degraded data. Okay, let's go to the results related to the federated learning. Here we evaluated 2 distinct federated learning aggregation strategies. The first one, as I mentioned, this is just the averaging of all the parameters of the model, and the second one is a geometric median, which is more you need more computational resources because it's just it takes more time to calculate this geometric median function. So in this use case, we employed 10 local units, which possessed the data of various quality affected by the packet losses from 1 to 20%. And then we cross-evaluated the performance of multiple training and testing cohorts. For example, we trained our machine learning model on the original images, and then we consequently tested it on 1, 2, 5, 10, and 20%. And this is just another example how we trained and then tested our machine learning model. So here you can see that if we use the geometric median, the performance on average is better. And another conclusion here is that it's also important to make your retraining data as diverse as possible if you want it to be more robust to the degradations in the video. So yeah, this is the conclusions from these results. So here, a small summary about the advantages of employing this transfer learning and federated learning to enhance the machine learning robustness in industrial applications. So our transfer learning approach allowed to enhance the machine learning performance demonstrated on the data of right quality, which makes it feasible to employ. And then our federated learning demonstrated comparable performance to our transfer learning, but allowed also to enhance the security and privacy of the ITS users because of the inherent features in this federated learning. We keep the data private and we never transmit it, so we make it more private and more secure. And here we also can see that the transfer learning can be employed in the combination with the federated learning as the initial training procedure instead of training machine learning model from scratch. And this is also the point to the optimization. So we can spend less resources and less time if we can employ transfer learning for retraining the model. So yeah, let's go to the actual security part where we explore the vulnerability in the conventional federated learning architecture. For this, we need to get back to the conventional federated learning architecture and remember the 4 steps that we have. And let us assume that one of these local units were compromised by the adversary. So here on the first step, we perform the local training, then we send our updates to the aggregation unit, and then we aggregate our updates and send the global model back. And here, as you can see, if one of the local units, if at least one of the local units were compromised by the adversary can gain access to this global model. And let me try to explain why this is bad. First, the global model is aggregated based on the local models from all the local units participated in the aggregation round. And by gaining the access to this global model, the adversary can implement some kind of data inference attacks against this global model. For example, this might be a membership inference when the adversary is able to tell if the particular data sample is from the particular client. Next one is training data properties inference, where the adversary is able to extract some kind of sensitive or confidential data about the data set. And then the training samples and labels inference, when the adversary is even able to reconstruct the data based on the model only. And there were some successful attempts to do this. As you can see here, these guys in the publication number 3, they were able to reconstruct the images from the training set based only on the model, which might be really dangerous for your data. And as a result here, we have the privacy violation of all the local units participated in the aggregation round. And here we also need a strategy to address it. And let me introduce our financial use case where we introduced our approach how we can handle this problem. First, we already learned that the conventional federated learning possess vulnerability that may jeopardize the user's privacy and security. And our solution here is to employ our reputation and trust-based mechanisms, which we introduced in our previous research. And we need these mechanisms to accumulate the extracted knowledge on the quality of local units models and to employ them to drive the aggregation procedure. So let me quickly introduce our approach in details. First, we have the number of local units, and we have the local training here, and then after the local training, we send our models for aggregation. But before this aggregation, we introduced our novel step, which is called local models pre-processing. So let me go into a bit more into details. So as I mentioned before, the models might be, the parameters of these models. For example, there might be weights, biases, or gradient updates, or whatever you want, depending on your machine learning application. And here we can do the clustering of these machine learning parameters transmitted to us for aggregation by all the local units. And in our use case, we employed the unsupervised clustering, just k-means, but there might be much more complicated algorithms. And here we need to we first need to cluster these models, and then we need to calculate the distance of this major cluster of all the models. Distance to all the models from this from the center of this major cluster. And then we can decide if the model parameters lie out of the major cluster, so the unit might be potentially compromised. And then based on this distance, we can exclude these potentially compromised local units from the global model's distribution. But here, if we use only the clustering, we might have the problem. This is actually, as our experiments showed, this approach is too strict and leads to high false positive rates in detecting the compromised local units. And here, as our solution here is that we can accumulate this data on models provided with our reputation and trust indicators. And let me actually introduce the idea of this reputation and the trust. These concepts are actually really close to the reputation or ratings which are used in electronic commerce applications. For example, in Amazon or in eBay, you have the rating of the sellers, and users evaluate the seller based on his or her behavior. And here we also have some kind of similar approach, but here we don't have users which will evaluate the seller based on their activity. We need to do this based on our clustering approach. And here the reputation is an indicator which accumulates the quality of the models provided by these local units from the Federated Learning system from the start of working in the system. And in other words, this means that the better quality of the models the local unit provides, the better reputation it gains, and vice versa. And we also have the second indicator, which is called trust. So essentially, we can use only the first one, the reputation. But here we need to trust to do the decisions of the compromised local units in more convenient way. So using trust, we can just regulate how sensitive is our trust towards the local units based on the changes in their reputation. So here, yeah, I have some formulas. Don't worry, they're not too scary. So first, in the first step, we calculate the distance from the major cluster to all the local models. Then in the first aggregation round, we calculate the initial local units reputation according to this formula. And then in the next consequent aggregation rounds, we calculate the reputation of the models according to these formulas. First, we need to establish the alpha. This is kind of threshold. And if our distance is higher than this threshold, then the reputation of the local unit grows linearly. And then if the distance towards the model parameters from the major cluster is less than this alpha, the reputation declines exponentially. And this kind of approach allows us to motivate the local units to provide positive contributions into our learning process. And it takes only one or two negative actions to ruin the reputation, and it's kind of discourage the adversary to do this because we can easily identify him or her if they provide the negative contribution. Okay, on the step number 4, we calculate trust, and then on the step number 5, we compare our trust indicator against the established threshold, and we have the same if this trust is below than the established threshold beta, then we exclude our local units from the aggregation, from the global model distribution, and from the further communication. Here you can see our use case study design. In our use case, we have the financial use case with the SWIFT transactions. We have real industrial data with the kind of hard structural relationships that are hard to comprehend by the state-of-the-art machine learning models. And this data has around 4 million records on the financial transactions between various banks and more than 20 attributes, and the classification target for us is to detect the anomalous transactions. Here you can see the examples of the attributes. There are around 27 or 28 attributes, and initially the data set is highly imbalanced, and we employed some kind of pre-processing methods to make it more balanced. First, we feature engineered 2 additional attributes from the existing ones, and then we employed small library. This is a Python library to make our data more balanced and to avoid oversampling. So here you can see our results. First, we wanted to explore which machine learning architecture would be better on this data set in the centralized way, and we explored the random forest and the simple deep neural network architecture with the 4 layers. And as you can see here, DNN works better than the random forest, and in our federated learning, we decided to proceed with this deep neural network. So here you can see the result of the employing our reputation and the trust indicators against the conventional federated learning. And here, as you can see, that our approach demonstrated better result, even better than than in the centralized manner. And here you can see just the zoom version of this most important false positive and true positive rates in the industrial applications until around 0.3 false positive rate. Briefly about the advantages and limitations of our approach. First, it allows us to track how the quality of the models provided by the local units changes throughout the learning process, which might be employed in some kind of security audits and for other maybe security stuff. We can do the analytics, which is also good. We have more data. Then it allows us to detect the intelligent adversaries who might implement the non-obvious attack strategies. For example, there might be on-off attacks. The adversary might do a few positive actions, 1 negative action, and a few positive actions, and this is really hard to detect as some kind of smart adversaries. And our approach with the reputation decline in the exponential manner allows to address this problem. And also the accumulating of knowledge is more reliable than one-time local models evaluation. For example, we can do only the clustering of the models, but in our approach, we also accumulate the data on this clustering using our reputation and the trust, and this is just more reliable than using only the one-time evaluation. Also about the assumptions, our approach requires the active adversary that performs data manipulations, which can be detected by our reputation and trust-based approach. So in our case, unfortunately, we cannot detect the passive adversary, which will only listen to the ports, and yeah, we have nothing to do with these other approaches needed to be employed. This is just the summary of our major products and publications developed in our research. First, we developed our reputation and the trust methods that allow to enhance machine learning application security and robustness to data quality operations. Then we implemented these approaches as software prototypes. So we also produced 2 research papers and 1 patent applications based on these investigations, and we also have our software prototypes. And as I said before, we're open for the collaboration, so please reach out to us if you are interested in our research. We will be happy to talk about it and discuss any potential opportunities. So I hope this was not too boring. This was a more academic presentation than industrial presentation. I apologize about this. I tried to add some kind of fancy animation to the slides so to make it more fun. So thank you very much, and we'll be happy to answer your questions. Yeah. Thank you. Yeah, sure.
When you identify the folks who are potential bad actors, do you still take their data in sort of a less weighted, their models in a less weighted format, or do you eliminate them altogether?
First point here that we do not need the data. We need only their models. Yeah. We do it based on the clustering, and then based on this distance from the major cluster, we calculate our reputational trust indicators. And then if the trust towards the particular local unit declines below the specified threshold, we just exclude them from the aggregation procedure. We do not communicate with them. So after this point, so. Okay.
Still take their data,
No.
their model into account?
No,
So
we do not take.
I was just curious if you were worried about bias of the global model based on your initial clustering.
There might be a problem, yeah, if we have, for example, only 5 or 6 local units, that we might introduce bias. But here we need to assume that the model provided by these local units might be compromised. And so there's always a trade-off between the bias and the security. So we need to make the decision, and sometimes these decisions might get our performance lower and might get our model more biased. But here we address the security problem. So yeah, there's also a trade-off, and this is a really good question that researchers is trying to investigate now. So thank you for your question. Very good question. Okay. Yeah, sure.
Does the Federated Learning or also your reputational adjustments for it, does this handle model creep better? Like, when models trade for a while and go away from their initial training? You can get from like a dog to a cat pretty easily. Model creep.
You mean that can we achieve more performance if we use the Federated Learning, or?
Just the state.
It's referring to dynamic data sheet.
Yeah, data.
Oh.
That it gets.
I see.
Over time because it's easy, it takes a lot of small changes.
I see. Yeah, actually, the Federated Learning can better address this problem because of this aggregation procedure incurred in this. So we just make an average or any other strategy that we can use for aggregation of these models. And yeah, this is much more robust to the outliers comparing to the centralized model. So yeah, basically the answer to your question, yes, the Federated Learning can handle better these data shifts in the models.
Jason's question there is,
Okay.
I don't know if you've heard, like when Unity Gaming System had that problem with their model training recently, where they had their, I think it was their ad prediction tool or whatever, where they assigned ads to other people, they lost tons of revenue
Okay.
because they did it wrong. So they were taking effectively a trusted data source that was wrong.
Mm-hmm.
So, and it flooded it pretty quickly,
Mhm.
ruined their model. And
Yes.
so they lost $5 million in a quarter. So I don't know, they dropped the revenue. I remember seeing some news, I can't remember the details. But I don't know, so this is the opposite of creep, right?
Yeah,
You've got
sure.
a big amount of data from a trusted source.
Yep.
And I don't know if this, maybe because it's so distributed, and a lot of inputs,
Mhm.
maybe it wouldn't happen that way. But I know they had that problem. I don't know if this would handle this better because you have, besides reputational, you have a way to identify out-of-bounds data, sort of thing. I don't know.
Unfortunately not, because in Federated Learning we assume that all the clients should be anonymized and we don't have access to their data. So we can work only with the models. We don't have any access to the data, and that's,
So you can really just kind of identify that you got
yep,
two of bad state actually work or something.
Yep.
Back there and start again.
yeah, well, we can work only with the models. So yeah, based on the models. So, yeah. That's good. Thank you for your question. Okay. Yeah, I think you also had a question, right?
Oh, I was just wondering if, through the process, you have whitelists and blacklists. I know that you kick the bad
Yep.
actors out.
Yep.
You keep track of that so that if they somehow crop up in a different location or on a different device or a different, what prevents them from switching to a different device and becoming a bad actor as well? And are you able to detect those patterns based on previous submission, or do you not do it that way? You just, when they're bad, you just kick them off, and that's all there is to it?
Yeah, in this our approach, we just kick them off, but in any kind of real-world applications in federated learning, we usually know which devices participates in our kind of a federated learning setup, and if we see that we already kicked out one of the devices and the new device cannot be just added to this to the learning without our kind of permission. So yeah, this kind of, we know how many devices we had initially and how many we kicked. So yeah, we have this kind of knowledge, but in other applications, we might use other kind of patterns to detect them. So yeah, this is also possible. This, from the security perspective, this is a good question. Yeah, thank you. Good. Thank you.